Okay, so welcome back, guys. So in this video here, I'm gonna show you guys an example that tie both lesson 4.1 and 4.2 together. So it's gonna take maybe more than 10 minutes. I'm gonna try and just cut it short at 10 minutes here. So let's get to it. Let me zoom in a little bit. So example. Okay, so given a function, so given f of x equals x to the third minus 6x squared plus 9x plus 1. What we want to find first is part A. Let's go ahead and find the interval where f of x is increasing or decreasing, or n. Okay, so this will be from lesson 4.1 there. Part B, let's find the interval where the function f of x is concave up or concave down. Okay, so this is from lesson 4.2. And then furthermore, part C, find the inflection point, if there's any, f of x. Okay, and then this would be from lesson 4.2. So when we find the inflection points, so that's using in a coordinate, like x comma y kind of deal. So order pair. So we want to write that as order pair. Okay, and then lastly, part D, we want to tie another concept from lesson 4.1, and that is does f of x have any local extrema? So remember that means a local min or local max. Okay, so that's from 4.1. So let me just go highlight. So this is lesson 4.1, 4.2, 4.2, and this is 4.1. So we're going to try to tie both of those lessons together in this example here. So let's do it. Okay. All right, so part A, to find the interval where the function is increasing, decreasing. Remember from lesson 4.1, we learned that the first derivative tell us where the function or the graph is increasing or decreasing. So to do that, we start out by taking the first derivative. Okay. All right. So to find out where the function is increasing, decreasing, we need to find this here. So set f prime of x equals 0. And to solve this equation is like find the critical value. So this is like find the critical value. Critical value. Okay, that's what we're trying to find, the critical value. Okay. Find the critical value or values. Okay. All right, so that means 3x squared minus 12x plus 9 equals 0. Factor out 3, we get x squared minus 4x plus 3 equals 0. Divide by 3, that gives us x squared minus 4x plus 3. Factor that, give us x minus 3, x minus 1. Therefore, the critical values are 3 and 1. Okay, so we'll say those are the critical value. Okay, and now we're going to plot this on a number line to find where the function is increasing, decreasing. So we're going to say we're going to do first derivative sign chart. Okay, so that means draw a line and plot these two critical value 1 and 3. So let's say this is from negative infinity to 1 for that region, 1 to 3 for that region, 3 to infinity. And remember, we're going to pick test point to determine where the function is increasing, decreasing by looking at the signs of the first derivative, hence why it's called first derivative sign chart. So we're going to say pick x equal to 0 in this case, pick x equal to 2, pick x equal to 4. And we're going to plug these values into the first derivative functions or formula to determine the signs of the first derivative. So I'm going to go ahead and use this reduced form here. So I'm going to go ahead and plug the x value into that. Okay, so I'm going to say 0 minus 3 times 0 minus 1. So we're looking at negative times negative. So that's going to be positive, and that's greater than 0. So that means the first derivative is greater than 0. That means f is increasing. This is from less than 4.1. All right. Let's do the same thing for x equal to 2. 2 minus 3, 2 minus 1. So we're looking at negative result, positive result. So that means we're looking at negative overall. So that's less than 0. If the first derivative sign is less than 0, meaning it's negative, that means, so let's just go ahead and say f prime is less than 0. So the function is decreasing. Okay. And then finally over here, let's plug in the 4 into the first derivative. 4 minus 3, 4 minus 1. So that's positive. That's positive. So that's equal to positive greater than 0. F prime of x greater than 0. Therefore, f is increasing. So I'm going to go ahead highlight the region of the interval on the x-axis or the horizontal x-axis that the graph is increasing. Let's use blue. So the graph increasing from negative infinity to 1, and then from 3 on to positive infinity. And the graph is decreasing from 1 to 3. Okay, so let's go ahead and write that as the answer. So we said f increase on negative infinity to 1 union 3 to infinity, and f decreases on 1 to 3. So those are the interval where the function is increasing and decreasing. So that's just part A. It's pretty long there, but you know, those are some good work there. Let's move on to part B. Part B, we want to find out where the function has changes in well, the function concave up and concave down. Okay, so let's find those intervals. Okay, so part B, okay, to find where the function concave up or down, we set second derivative equals 0. So this is like finding the critical value, but it's kind of like finding the critical value for the second derivative. So let's make that note there. So it's kind of like finding critical value for second derivative. And this will tell us about concavity. So let's find the second derivative. So we had the first derivative already, which is this one. So let's just gonna follow that. So we know that f prime of x is 3x squared minus 12x plus 9. So therefore, second derivative is just gonna be 6x minus 12. We're gonna set that equals 0. That means x is equal to 2. So now we're gonna draw. So now we're gonna draw the second derivative sign chart. So this would be another thing that you need to write down on your note card. So the second derivative sign chart will tell us about the concavity of the function. So this will be describe the concavity. And then over here, first derivative sign chart, this is increasing or decreasing. Okay. All right, so let's do it. First, we plot the critical value for the second derivative on a number line. So here's 2. So that break the number line into 2 region, negative infinity to 2 to positive infinity. All right. So, and we're gonna pick some test point there. So let's pick x equal to 0 there in that region, maybe x equal to 3. All right. And then we're gonna plug these test point into the second derivative to test the sign of the second derivative. So remember, way from the beginning of this lesson, we conclude that if the second derivative sign is positive or negative, that would tell us whether the function is concave or concave down. Now notice that you can do this one single chart there. If you have this, and then you have that, meaning second derivative, and then first derivative, and then the function. So you can do this in a single chart there, but we break this down to 2 separate charts so you can see the step there. All right, so let's plug these test points into the second derivative. Okay, so the second derivative is 6x minus 12. So we're going to plug in x equals 0 for the second derivative. Okay, so that's going to give us a negative sign. Negative is going to be less than 0. So this tells us the second derivative is less than 0. If the second derivative is less than 0, that means the function is concave downward. Okay. So we'll say f is concave downward. Okay. Over here, let's plug 3 into the second derivative. So that's going to give us 18 minus 12, and that's going to be a positive number. So a positive number means greater than 0. That means the second derivative is greater than 0. If the second derivative is greater than 0, that means f is concave upward. Okay. So now we have the answer as, let me go ahead and highlight this here. So concave downward, concave upward. So now we can tie this up. We can say f is concave downward on negative infinity to 2. F is concave upward on 2 to infinity. So at this point here, guys, at this point here, the function at this point 2 there, the function changes the concavity from downward to upward. So there we have it. Part C, the inflection point occurs at when x is 2, because we have concavity change at that point, to whatever the y coordinate, which is f of 2, whatever that is. So this is the inflection point there. Okay, so once we have concavity changes, we can just we can determine the inflection point pretty simple there, pretty easy. So let me go ahead and write. So you say inflection point occur at 2, f of 2. So I'm going to go ahead and skip part D. I'm going to let you guys figure out part D on your own. So just review 4.1 notes, then you can find those local extrema there. And I think I'm going to pause the video, this lesson on this last video here. I'm going to wait till we go on Zoom and discuss the last thing, and that was what is the business application of inflection point, that is point of diminishing returns. So we'll come back to that on Zoom there. Okay, sorry, this video is a little bit long. It's 14 minutes long, more than what I anticipated, but I think you can manage it.